In mathematics, the convolution theorem states that under suitable conditions the Fourier transform of a convolution is the pointwise product of Fourier transforms. In other words, convolution in one domain equals pointwise multiplication in the other domain. Versions of the convolution theorem are true for various Fourier-related transforms. Let M be two functions with convolution. Let denote the Fourier transform operator, so and are the Fourier transforms of n, respectively. Then where denotes pointwise multiplication. It also works the other way around. By applying the inverse Fourier transform, we can write, and note that the relationships above are only valid for the form of the Fourier transform shown in the proof section below. The transform may be normalized in other ways, in which case constant scaling factors will appear in the relationships above. This theorem also holds for the Laplace transform, the two-sided Laplace transform in, when suitably modified. For the Moline transform and Hartley transform, it can be extended to the Fourier transform of abstract harmonic analysis defined over locally compact abelian groups. This formulation is especially useful for implementing a numerical convolution on a computer. The standard convolution algorithm has quadratic computational complexity. With the help of the convolution theorem and the fast Fourier transform, the complexity of the convolution can be reduced to O. This can be exploited to construct fast multiplication algorithms. Proof. The proof here is shown for a particular normalization of the Fourier transform. As mentioned above, if the transform is normalized differently, then constant scaling factors will appear in the derivation. Let f g belong to L1. Let be the Fourier transform of and be the Fourier transform of, where the dot between x and nu indicates the inner product of Rn. Let be the convolution of, and now notice that hence by Fubini's theorem we have that so its Fourier transform is defined by the integral formula. Observe that and hence by the argument above we may apply Fubini's theorem again. Substitute, then, so. These two integrals are the definitions of an, so, QED. Convolution theorem for inverse Fourier transform. With similar argument as the above proof, we have the convolution theorem for the inverse Fourier transform, and functions of discrete variable sequences. By similar arguments, it can be shown that the discrete convolution of sequences n is given by, where dtft represents the discrete time Fourier transform. An important special case is the circular convolution of n defined by where as a periodic summation. It can then be shown that, where dft represents the discrete Fourier transform, the proof follows from dtft #periodic data, which indicates that can be written as the product with is thereby reduced to a discrete frequency function. The inverse dtft is QED.